I live in San Francisco, and about 4 weeks ago now, I was at a performance in Berkeley, the Berkeley Repertory Theater. It's a more modern interpretation of a Bertolt Brecht play on Galileo. And I enjoyed the play very much. I thought it was very well done. I remember reading it years ago and enjoyed it then, and I enjoyed the repertory company's performance. There's a very, very powerful scene there where Galileo, this individual who, throughout his life, he was constantly trying to seek to improve his status, his station in life. He was always trying to do that. There's no doubt about it. But his ego and also his brilliance kept running sort of aground onto religious shores. And there is one very, very powerful scene where there is a high official in the church who is sort of stamping around saying that the reason that the earth is the center of the universe is so that God can look at me. Solely so he can look down, he's not confused by anything else, and he can look at me. Now what I want to do is to take that idea and to look sort of through the ages to see how our position in the cosmos has been constantly displaced from the center. Now eventually we're going to get around to the idea of, is there a center to the universe? No, there's not. And where are we exactly in this universe? I don't know, no special place. But what I want to do is to take you through this in a relatively quick fashion, because we've only got a few minutes, but we're going to cover as much as we have all of human thought on this, and I've done it in the form of a roughly 6-act play. And I just want to sort of go with that, and we'll see how these things develop, because it is an interesting study in the human creature to see how we always want to be at the center. And with updated information, even past the epilogue that you're going to see here, again, we find ourselves trying to sort of carve out a special little niche in the universe for ourselves. So let's begin by considering these ideas. Okay. Let's start a long time ago. And really when you think about it, this wasn't that long ago. When you talk about 2 millennia ago, when people talk about the time of Christ, when they talk about the Greeks, which are, let's say a few centuries BC, it's only roughly 100 human generations. Not that long ago in the past. So let's go a little bit beyond that. When our ancestors were finally starting to stand upright and they noticed that lightning and other things, bright things, fire, naturally occurring fire, because of lightning or something, they also saw tiny fires in the sky. So at some point there had to be one or a few individuals that actually stopped, looked up from whatever the kill was, or if they were on a hunt, or if they were making grass mats to sleep on, I don't know what. But they stopped and they noticed that there were stars in the sky. There were points of fire in the sky. That was the beginning. That was the beginning. And we don't know what they thought about these, because for them, just staying alive was the most important thing. That was the most important thing. But we do know that as time went on, we began to see ourselves as the me. We were there. We were the center of the universe. Act 1. Now, for this act, what you have to do first is go back to, roughly 200 years before the time of Christ, before the Common Era, and we run into an individual named Hipparchus. Hipparchus was a brilliant individual. We really don't know anything directly about him except what we learn about from an individual here in the lower right that lived in the 2nd century AD, roughly 400 years after Hipparchus. And what we know that Hipparchus did is he considered our place in the universe, among other things. He was the first person to actually look up at nighttime stars and say, you're pretty bright, I'm going to call you a 1. You're not too bright, I'm going to call you a 6. And he came up with the means of classifying star brightness. The other thing that he did is he tried to give us a place in the universe. And he imagined that we were at the center. The earth was firm, it didn't move. The celestial sphere, that great crystal latticework that exists outside the earth, that's the thing that moved. Any idiot can tell you that now. If we go outside and lay on the ground tonight and watch the stars, you don't feel the earth moving. You see the stars moving. You see the moon moving. So it's really not very difficult for me to imagine how it did seem that we were at the very center of everything that was out there. Hipparchus gave us a complicated cosmology, and you'll see what I mean by this in just a few minutes, where the Earth was at the center. And then you have in these perfectly circular orbits, the planets, the sun, the moon orbiting us. Everything was there surrounding us. I mean, the ultimate in egocentrism. But there we were at the very, very center. And Ptolemy took this idea, he wrote it up. He said, hey, Hipparchus had some great ideas, really good ideas. But what I'm going to do is I'm going to improve it because, you know, when we watch some of these objects in the sky, we notice that they move a little bit. The brighter objects, the so-called wandering stars, the planets, they seem to move in odd ways sometimes, especially one that sort of has this orange cast to it, Mars. It seems to move backwards sometimes. How do we explain that? So Ptolemy came up with this very complicated, well, on the shoulders of Hipparchus here, of saying that the planets and the sun don't just orbit us directly. They actually orbit us on epicycles. You have circular motion, and on top of that circular motion, you have smaller circular motion. And it gets worse and worse, because to explain the regularities, you start adding more and more epicyclic motion. You start making it more complicated. But for over 1,000 years, that is what reigned. That is what reigned. And if you say, oh my goodness gracious, you're right, because now, in this age of technology in which we find ourselves, something that might be 2 decades old is considered to be a good idea because it's got staying power. This was around for over 1,000 years, this idea that the Earth was the center of the universe. True, through the midst of this, you had the Dark Ages, and not a lot went on, not a lot of pleasantries went on, but yet Ptolemy's ideas stuck around until the 16th century. Until we move from this balcony at dusk with Hipparchus, and then a few hundred years Ptolemy out watching the stars, till we find ourselves in a damp, soggy bedroom. And let me apologize first. I just got my transparencies. That big black image that you see up there in the upper left, that should be the sun. I'm not sure exactly where the sun is now, but we'll say that it's night. And so you can just imagine your favorite image of the sun. What we find ourselves now, 16th century, 1543, let's put a better number with it. And this individual in the lower right, Copernicus, he's a Polish astronomer, mathematician, overall thinker, priest. I mean, he was everything pretty much rolled into one. All of these great thoughts, though, were not static. What he observed, based on his own observations and others, was that this idea of Ptolemy's seemed to be a little cumbersome. It seemed to be a little too complicated. There's this thing in science called Occam's Razor. And Occam's Razor says that, in general, you should always go to the simplest solution first. Nature seems to choose the simplest solution to a problem, or the simplest means of getting somewhere. And he came up with a cosmos that even he was a little afraid of. Because, like I say, it's 1543, he's on his deathbed. And he has a publication, and this publication he actually entrusts to a friend of his who's a priest. And he says, I want you to publish this, I'm almost dead. And the priest says, well, okay, I'll do that for you. But just to be safe, what that friend did is he put a little preface at the beginning of the book that said, these are just ideas, the ravings of someone that's almost dead, maybe a madman, hypothetical, but here it is for your consideration. And Copernicus dies on the day that it's published. The day that it's published. Now, if you were a scientist at the time, confronting questions of such a fundamental nature, a lot of times you found yourself at odds with the prevailing religious dogma, the religious ideas of the time. And remember, Ptolemy's idea had been around for a long time, with the Earth at the center of the cosmos, all the planets on these beautiful circular orbits. The circle is perfect. Perfect. And along comes this upstart who doesn't have the gumption to release his ideas any time before now, who comes out with this book that displaces us from the center of the universe. He puts the sun at the very center. And he moves us out to the, not periphery, but we're not at the center anymore. And this was a profound change. But just to show you how slowly this caught on, the Catholic Church didn't really recognize the power of this model, of this new cosmology, for about 70 years. It took about 70 years for it to make it onto their list of banned books. Things that you were not supposed to read. Not supposed to read. And I think, you always hear about the Copernican revolution. You hear other comparisons, people using that as this great adjective to compare it to other revolutions. But it truly was. Because for the first place in all of human history, as far as we know, we were not at the center of the universe. And when people started, other scientists, examining his ideas, people said, Copernicus can't be right. Because his model was still complicated. It was still complicated, and the observations at that time were not up to snuff. They simply couldn't make, or they didn't have the accuracies or the precision, that were needed to actually confirm that Copernicus might be right. A number of people wanted it to be right because it seemed so simple. But the interesting thing about it, and this is one of the neat things about science, is that he came up with this cosmology, and this model for the heavens, it made certain predictions. It said that, okay, if you've got the sun now is at the center, well, Mercury and Venus, goodness, he placed those between us and the sun. They have smaller orbits. And he said, one thing that you should see when you look at Venus is it should go through phases, just like the moon does, because it's closer. Sometimes we're going to see almost nothing. We're going to see its backside, the side that doesn't have any light striking it. Other times you're going to see crescents, other times gibbous. That was one prediction that he made, among some others. But that was the thing that really sort of knocked the pillars out of our idea of ever being special. Now we move forward just a little bit further in time. Move into the 18th and 19th century. And it is amazing to me, some of the leaps of imagination that humans are capable of. I mean, it really is. I mean, we really are very bright. I'm sorry. We really don't know a whole heck of a lot, but we still are very bright. And some of these individuals I'm sure you've heard of. The one over on the left is William Herschel, a great English observer. And his sister Carolyn, I mean, she was so devoted to her brother and to his observations of the heavens, and he made such large telescopes to observe. His son John, who took their efforts into the southern hemisphere and made observations. He had some very interesting ideas. Then up also on the upper right is a man that is most normally considered because of his contributions to philosophy, Immanuel Kant. And for this man that had certain philosophies that I find sort of attractive, I like to imagine him walking out on a dark road and looking up into the heavens. And in San Diego you can't do it, in San Francisco you can't do it. But I was raised on a farm in Tennessee, and you can do it there. When you're out and away from the stars, away from the stars, and you're never away from the stars, when you're away from city lights, and you look up, you can see the Milky Way. If you're in a dark location, you can actually see that there seems to be this milky fluid that's just been spilled across the sky. So imagine Immanuel Kant out walking with his hands behind him in sort of this nice philosophical mode. He stops, he looks up, and he imagines that we live in a disk of stars. I mean, when I was young and then 20s, I don't think I really had such a leap of the imagination. But he was wondering about the nature of the universe. And he said, you know what? When I look up and I see that big bulging thing right there, and I see this lane of light across the heavens, and they knew that those were individual stars. Galileo had shown us this in the early part of the 17th century. He said, I think we live in a disk of stars, just like two dinner plates put together. And we find ourselves sitting in the middle of it. Oh, what an idea. Herschel, he said, you know what? I think I can actually come up with what our universe looks like. I think it looks like a disk. And the way that he came up with that is he actually made star counts. He looked in that direction. He said, okay, in that direction I count, I don't know, about 40 stars. I look in that direction, I only count about 16. I look over here, I only count about 7. And he put all of those counts together, and he came up with something that looks like a disk. Now, what neither of these individuals knew about was the fact that space isn't empty. Space is filthy. It is full of stuff. They were just considering that stars, based on their brightnesses, were going to be, or have their light diminished only by distance. A really intense star, it's close. A really faint star, it's far away. And based on these observations, Herschel came up with this very attractive idea, but look where it places us. All of his star counts place us right at the center of the universe again. Forget the fact that in our solar system with the sun and the planets, we're not special anymore. But Herschel, he put us in the center again. Kant, he put us in the center again. There was another guy too named Thomas Wright, another Englishman. And I didn't put him up here because he got a little crazy toward the end. He initially said that the universe itself was, where we inhabited was sort of the volume between concentric spheres. It's just like imagining that we're in the fuzz on the surface of a tennis ball, and all that fuzz is the galaxy. He thought it was perfect and spherical and aesthetically, spiritually very pleasing. But then toward the later years of his life, like I say, he got a little bit crazy and he started saying that novae, exploding binary systems, are actually due to volcanoes in the sky, and the galaxy that we see were the meeting of two great shields. He really went off the deep end just a little bit. But I just wanted to mention his name because he was a contemporary, and he did influence, I guess, mutually all these people. And if you're wondering who Bowman is, My God, It's Full of Stars, 2001. Okay. Now, let's jump forward. Now we find ourselves in the 20th century. And I like this because I'm within a handshake of these times we all are. I mean, my granddad was alive at this time. And for me now, this becomes more real. The setting is a smoke-filled dining room in Washington, D.C. in April of 1920. We have a meeting of the National Academy of Science. And at this meeting, there's going to be a debate. There are actually going to be two questions considered, but only one of them we want to talk about here this evening. And by debate, now we have this idea that you have debate teams and the individuals get up and it's like, meh, 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 meh. Then you get over here and you make your counter argument. It wasn't like that. It was like a gentleman's gathering. One person gets up and presents his argument, and it was exclusively male. And then the other individual gets up and presents his argument. Very genteel, very genteel. But the question that was being debated was one of fundamental importance to us. The question was, is our galaxy, is the Milky Way galaxy all that there is? Is that it? And true, I'm showing you the Andromeda Galaxy here because we have never actually been outside our own galaxy to make images, but it's a little bit bigger, but we think it's roughly the same shape. The core is a little different, but for all intents and purposes, we're going to say that that's close to ours. There were two individuals that represented the two sides in this great debate. Now, and they both have great names. Here in the upper right, you've got Heber Curtis. He was at Lick Observatory here in California. And he was an individual that was actually on, it turns out, the correct side of the debate for the wrong reasons. Then over on the other side, there's a man named Harlow Shapley, who at the time, I don't think he was director of the Harvard College Observatory, but he was eventually the director of the observatory. He used perfectly sound reasoning, but he had bad data, and he came to the wrong conclusion. Now, what they were debating again was whether our Milky Way galaxy is all that there is. Is this the whole universe? Is this everything? They still weren't really considering the fact that there's a lot of crud between the stars, a lot of stuff, and you can actually see it here in this image nicely with these dust lanes. But they were debating this. Curtis said, we live in one island universe, to actually use Immanuel Kant's phrasing. We live in one island universe, what we would now call a galaxy. And all those little fuzzy patches of light that these people have been seeing for 2 centuries, that we call nebulae, that we call these little clouds, those are actually separate and distinct galaxies, like our own, but they're far away. They're not connected to us. They're far away. Now, over on the other side of the debate, you've got Harlow Shapley, who gets up and he says, sir, I'm sorry, I think you're wrong. Because I have data that actually show rotation in those distant clouds. I can actually see that they're moving. And you and I both know, if something is close to you, you can see motion. If I were to run 100 yards away and would start sort of raising my eyebrows, you really couldn't see it. You really couldn't see that very, very subtle motion that I was making. Well, it turns out, again, those data were wrong. And people to this day don't really know the individual that made the observations. He was renowned for making excellent observations, but they were wrong, and we don't know why. Well, all this is occurring in 1920. There's a young man who was, he was a lawyer by training. He was a basketball coach by avocation. He coached the Jeffersonville, Indiana basketball team to the state final. I don't remember if they won. I'm sorry, I should remember that. Going to Indiana University. But he got fed up with law. He moved out to Southern California, and he worked at Mount Wilson Observatory. His name was Edwin Hubble. And Hubble made observations at Mount Wilson that settled the debate. What he did, he looked at this galaxy, and he looked at a few others, but this was the first one, M31, Andromeda Galaxy. And what he saw, he could actually see individual stars, but he saw that a few of those stars pulsated. Just like that. Periodically they would get bright, then they'd get dim. And then with the same period they'd get bright, then they'd get dim again. And he was actually able to measure how long it took between just like that, on the order of tens of days. He was observing a special kind of variable star called a Cepheid variable. And years before, just at the end of the 19th, beginning of the 20th century, there was a woman named Henrietta Leavitt at the Harvard College Observatory that had stumbled upon, just serendipity, a relationship between how bright these stars get when they're big and puffed up and the time it takes them to puff up. She had stumbled upon a period luminosity relation. And this relationship, if you have how bright a star really is, it's like its intrinsic brightness, how bright it really is, you can compare that to how bright it appears in the sky. And the difference between those two gives you a distance. Hubble was aware of this information. He said, oh my goodness gracious, I know how long it takes these stars to puff up. I can calculate a distance. And what he found was that this galaxy was far away. It was not a part of our Milky Way galaxy. Now today we know that it's actually much further away than he estimated, and we also know that it is associated with our own galaxy because it's part of the same little local cluster of galaxies, roughly 24 galaxies. They're sort of like bees around a hive, just sort of falling around each other. But still it is a separate and distinct galaxy. And Hubble saw this for other galaxies as well. He solved the debate. He solved it. And again, what are we done? We've been displaced. We were at the center of the action again, and now all of a sudden we find that, our galaxy is just one of many. Now, based on, if you've seen this image called the Hubble Deep Field image and the Hubble Deep Field South image, estimates are that there are probably on the order of tens of billions of galaxies in the observable universe. We're one average sort of garden variety galaxy. But then Einstein comes along to the rescue. In 1915, Einstein released his general theory of relativity. And in the general theory, what he considered were motions, especially just gravity. What happens in a system that's accelerating, he asked himself. And he came up with this beautiful formulation of gravity. Beautiful formulation. That was very difficult to work with because there weren't many people in the world that could actually deal with it. But he had a gut feeling. And I'll be the first to say that Einstein was a brilliant physicist. He was a pretty good mathematician. Pretty good mathematician. The problem was, being a better physicist than mathematician, he really didn't believe some of what his math told him. He developed this theory. There were individuals that solved his equations of general relativity, and when you solve those equations, what you find is that the universe expands, it puffs up, it does it quickly. And he said, no. Intuitively, I know that is not true, because he was influenced by a few generations of scientists who felt that the universe was infinitely old, infinitely big, and static. It just sat there, aging. Everything just went on its merry way. So what he did is he actually introduced a new term into his equations called a cosmological constant. And he said, eventually, that was the biggest blunder of my life. I should have believed my math. Now, we'll come back to that shortly, too. But, goodness gracious, somebody else is missing over here. Oh, okay, that's not the sun. That's actually the cosmic microwave background, but that's something else. Up here, in the upper left, a Belgian abbé named Lemaitre. And Lemaitre actually solved those field equations. He said the universe expands, and he was really the first one to come up with this idea of a Big Bang. He believed that there was this thing called a primeval atom, and this primeval atom just broke apart, and those parts broke apart, and eventually you ended up with the matter that we know and love today in this overall expanding universe. Einstein said that's ridiculous. I don't believe it. I don't believe it. See, I've even changed my equations. It's impossible. There was a meeting on Mount Wilson Observatory. Lemaitre was there, Einstein was there, and Hubble was there. And I imagine the three of them sitting around the table. And Hubble comes up. He slides his notebook across the table to Dr. Einstein. Maybe there are a few sort of crude black and white photos that he's made of M31 and other galaxies. And what Einstein does is he looks down and he says, this is the most beautiful thing I've ever seen in my life. Because Hubble, again, it seems like he was never out of the center of activity. He had made observations of galaxies at increasing distances from us, further and further away. And what he did was, he found that those galaxies were moving away from us. Every distant galaxy he observed was moving away. The ones that were closer were moving away from us a little bit slower than those that were far away. And those that were really far away were moving away from us the fastest. His observations directly showed that those things, those galaxies, it wasn't that they had a speed, it's that like space between them was expanding and was blowing them apart like they were riding the crest of these great space waves, pushing them apart. And Einstein said, my gosh, I mean, it really does expand. And it was at that meeting that he changed his mind. And he said, I should have believed what my numbers told me all along. But now think about this. We've got an expanding universe. We look out in every direction, and the distant objects that we see are moving away from us. What do you infer from that? We're at the center. Oh, goodness gracious. Strike up the band. We're at the center again. Everything is moving away from us. Now, that has, I mean, that can be sort of bad too. Why is everything moving away from us? Are we at a bad place in space? Yeah, really. Yeah, there's something wrong with us. Yeah, for some reason, nothing wants to be around us. That is the first thing. First of all, oh, gee, wow, we're at the center again. It's like, oh, boy, what? Why? And to get around this, what you have to do is you actually have to examine what general relativity tells us, what the solutions tell us about an expanding space. One thing that's built in to modern cosmology, and there are exotic cosmologies that might not consider this, just to see what could happen. But one thing that's built into all of our ideas of cosmology is something called a cosmological principle. And that says that there is no preferred location in the universe. None. There's no special place. There is no center. There is no center. Now, that's something that's sort of heady to consider. But without that, if you find that there are preferred locations in space, you find that your physics starts to behave just a little odd if you can have special places. Now, there are models that have been birthed to try to explain, or analogies that have been birthed to try to explain an expanding cosmology. There's a so-called raisin bread cosmology, where you've got raisins in a loaf of bread that hasn't been baked yet. And they're all a certain distance apart. You put them in the oven, and during the baking process, they all move away from one another. And when you pull the thing out and you look and you say, my goodness, the raisins are the same size, but they're further apart. And if you could locate yourself at any of those raisins, during the baking process, you would look at it and you'd see all your raisin buddies moving away from you. It doesn't matter which raisin you pick. You'd all be moving away from each other. Now that's sort of the idea of expansion in a nutshell, and we can certainly talk about that in greater detail. But we found ourselves not at the center of the universe. We really didn't. We were displaced again. Now, where do we find ourselves? There are theories, no, there are hypotheses that exist concerning the universe and our place in it. Why does the universe exist? How does it exist? How did it come to exist? And one of the most important questions is, why does the universe exist the way it does? It seems to be just right for us to be here to observe it. If you were to change just a few quantities in nature, if you were to take the mass of the electron and change it just a tiny bit, life as we know it wouldn't be here. The mass of the proton, I mean, we're loaded with protons. If you change it just a tiny bit, we're gone. If you change the forces in a nucleus, in an atomic nucleus, if you change those forces a little bit, we're not here. So why does the universe exist in the way it does so that we can have gatherings like this, nice intimate gatherings like this tonight? Why we can lose spacecraft around Mars or even send things to Mars and stuff like that. Why does it exist the way it does? Now, all of this is embodied in the so-called anthropic principle that tries to get at a universe, or trying to understand a universe that seems to exist for us. And there are multiple, just an incredible number of universes that we think could exist. Do they exist? We don't know. Right now you hear all this stuff bandied about our universe is now written with a lowercase u rather than a big U for the universe and everything. It's a lowercase u, and it's one of but maybe an infinite number in a larger multiverse or a metaverse. We don't know, because we are confined to this universe. We can't get outside, as far as we know. Can't leave it behind. I mean, we're stuck here. So right now what we're left with is sort of dreaming about what these other universes would be like. Are there going to be creatures there like us? Is physics going to behave the same way? We don't know. This is the only one we've got to deal with. What came before our universe? Was there another universe that had physics like ours? I don't know. We don't know. That's one of the important questions that will probably be addressed within the next 20 years, because people are considering now, what actually came before our universe? What's going to come after? Because right now it looks like we live in a universe that's going to expand forever. We don't seem to have enough material inside to stop this expansion. And again, I appeal to aesthetics, and I say that's just not too pleasing. For some reason, I want closure. I want to know that the universe is going to die just like I am. But that doesn't appear to be true. It just doesn't appear. And let me just add, before I go to the last little point here, that again, with the anthropic universe, this anthropic principle, it again centers us. It brings us back to a universe that seems to be built just for us. And I'm sure, 1,500 light years away, there's some creatures in an auditorium, and they're talking about how the universe is existing just so they, in their multi-tentacled body, can experience it. I'm sure. I'll wager. But there are other things now. There's I guess, other things going on that tend to do this too. If you have not heard about the discovery of planets around other stars over the past 4 years, you've really missed out. Because now we're up to almost 20 planets around other stars. More than twice the number that we have here in our own solar system we now know exist out around other stars. And supposedly by the end of the year there's going to be another announcement. Another 6 have been discovered, another 6 planets. The universe seems to be teeming with planets, or at least our galaxy, the stars in our area seem to be teeming with planets. Big planets. We can't see the small ones like Earth yet. But what we're finding when we look at these objects is that most of the orbits of the planets appear to be very elliptical, very squashed circles. And now we ask ourselves, gee, when you look at the planets in our solar system, most of the orbits are almost perfectly circular. True, there's some deviations, and Pluto is extreme in more than one case. But we seem now to be in a solar system that's different. We always search for uniqueness. And this time, that just, even though the data might indicate that we are, and maybe we will be, maybe we're out in the tail and we're not in the sort of the main part of the bell curve, but we always tend to want to be at the center. And in spite of, or in addition to, all of these questions and our sense of place in the universe, I don't know, in relativity and extrasolar planets, it's funny that over these past, I don't know, what do you want to say, several hundred human generations, we find ourselves back where our ancestors were all that time ago. Now we have, maybe we can enhance our abilities just a little bit with binoculars, but you don't need binoculars. And the response is the same. Ugh, cool. It's just the same response. So regardless of where we really are in the cosmos, it's still a pretty special place. Okay, thank you. The question is, do people really take anthropic principles seriously?
Like someone being astounded that the sun comes out in the daytime.
Yes, people actually do. And, but again, when you're working in cosmology, when you're working pretty much at the edge of human knowledge and at the edge of technological, mathematical, or at the edge of our tools, what you find yourself sometimes are confronting questions that are not necessarily physical or have physical answers. And for the other scientists in the room, you might disagree with this, and I would certainly be happy to talk to you about it. But what you start confronting are questions of that are generally more metaphysical in nature, that possibly are religious in nature. And there are a large number of closet cosmologists that do consider this. They do sit around and ask themselves the question, why does the universe exist just so I can perceive it? Now, I mean,
my response to that is most religious questions are not real serious questions.
Oh, really? Oh, I disagree. Oh, really? I think it gets at the heart of meaning, though. It gets at the heart of place. I mean, we all look for place in the cosmos. And, I'm not trying to take any side, or I can take a side here. I think we all try to ask the best questions that we can for ourselves. For a scientist is equipped with different tools to ask questions. Someone that's in religious studies, or someone like the speaker next week, I think you're going to find in that case an interesting blend of background and tools. So I would disagree. I wouldn't say that those questions are always silly because they get at meaning.
Asking a question that can't be answered seems like a waste of time.
Oh, really? But so many questions that are asked. But isn't that some of what makes us human, is the ability to ask questions? In trying to find the answers, a lot of times we find new questions that do have answers.
Oh, it's okay to ask questions. The technique you use to answer those questions is even more important, whether your answers are valuable or not, or sensible. And when it comes to cosmology, religion seems to have a talent for getting it wrong every time.
Well, I have a question then. It's interesting to me that when scientists consider religious questions, a lot of times, for those that are trying to bring the two together, why is it that often they don't turn the same scientific skepticism and scientific, what's the word? They don't turn the same level of, somebody help me here, of critical thinking to answering or to what they're examining. I mean, that's the other side. That's why I said there are a lot of these closet cosmologists that consider questions like this. Because it seems like they don't they don't treat religious questions with the same amount of critical thought. And they should. It might be one of those silly questions, but no, I'm not being facetious either, because I mean some people do consider it a silly question because all we can examine is what we can see here in this universe. But I think some of the math that we can actually use to describe our universe has suggested there are interesting possibilities, and that is that you can actually have other universes, other dimensions. We are creatures that are intimately tied to our 3 dimensions. I mean, I can go anywhere I want to in 3 dimensions. I can jump up and down, I can go left and right, anything that I want to. But I'm tied. Now, if we talk about life in 2 dimensions, and you can say, oh, I can imagine that. I know what it would be like to be in a sheet of paper. That's not 2 dimensions. We can't imagine effectively what 2 dimensions are. If we talk about life in 1 dimension, oh, it's life on a line. I can imagine I can go back and forth. No, because you can't imagine something infinitely small, except in 1 dimension. We can't do it. And now all of a sudden what we confront is the question of our 3 dimensions, space is expanding. What's it expanding into? It's expanding into at least another spatial dimension, or just some larger multidimensional space. Now, yeah, you sort of sit there and you go, because I can't imagine 2, I can't imagine 1, I certainly can't imagine 4. And I can't imagine 10 or 11, which some elementary particle theories actually require, are multiple dimensions. So what are we expanding into? We're expanding into another dimension. I'm not talking about the dimension of time. I'm talking about another spatial dimension that's different from height and width and depth here. I'm talking about one that's perpendicular to those. Now, there are many analogies that I can come up with. I can blow up a balloon that has pennies taped to it. You know, you've seen this. And the pennies stay the same size. Those are like the galaxies. But as you blow the balloon up, all the galaxies are getting further and further away. And you can see that balloon is blowing up into 3 dimensions. What you have to do is sort of say, okay, now wait, let me see if I can get this. Now we've got our 3 dimensions are like the surface of that balloon. We're actually warped somehow. And we're now puffing up into something else. That's what it is. Mathematically, it's actually pretty easy to talk about. I mean, you can talk about volumes of hypercubes and hyperspheres and things like that. But up here, we are 3-dimensional creatures. And I don't know if that is any more convincing or not, because it's the kind of thing that I lie awake at night and think about. I mean, it really is. It's like, how do you imagine? How can you explain it? How do I understand it? But that's it. I don't know if, because we really do, I think, like to think that because there is this expansion going on, the universe is expanding away from some central point. There was this big explosion in the past, and what you had is that all of matter was sort of thrown out into the cosmos. And that's not it at all, because the cosmos didn't exist. What was thrown out was all of matter, but also all of space, too. So if you want to say, where's the center of the universe? There, inside me, everywhere.
So all of space was thrown out into another dimension?
Yeah.
And this expanded into that other dimension.
Doesn't that sound hokey? I mean, it really does. It really sounds hokey, but that's what it looks like. And do we think that there are other dimensions? Yeah. And like I say, there's some theories that require other dimensions. I mean, they require them to explain some of the things that we see going on in very small scales. Subnuclear scales, small particles. They have certain characteristics that can only be explained if we say that there are other dimensions that exist, dimensions that we cannot touch or experience directly. Oh man, it's great stuff. It really is. I mean, and really, this puts us at the very limit of our ability to understand. At the very limit. Yes, they were. And this is one of the situations where we've actually had to sort of wait for technology to catch up. The techniques that are used, the Doppler effect. You look at a bright star. You know, you've got a star up here in the sky. And if someone were a few light years away watching the sun, what they would see is that it had a slight wobble back and forth in the sky. And that wobble is due to Jupiter orbiting it, because these two bodies are pulling on each other. An analogy that I've heard that I really like is to imagine, in the past, I don't know if there's still balls or not, but you can imagine all the gentlemen wearing their tuxedos. You know, they're wearing their black outfits with their long tails, and the women are wearing white gowns. And you're in a ballroom with very, very low lighting, so that really all you can see are these white dresses just sort of going around. Now, the analogy, that was actually applied to looking for black holes, but the same thing is true, because what we're looking at is something that is being affected by something that is pretty much unseen to us. We are inferring their presence. Now, there's one possible direct observation of an extrasolar planet or a planet around another star, but we rely almost exclusively on inference from these Doppler shifts. You know, we look at the star wobbling, and from the amount of the shift, we can determine, we can estimate the mass of the worlds. It's pretty crude. We can estimate the mass of the worlds, and we can also get an idea about how far away they are from the planet. So that's the general technique. What we've had to wait for, though, is sufficient, it's called resolution, in our spectroscopic information. Because the shifts that we're talking about are very, very subtle effects. Very subtle effects. I mean, we're talking about speeds around the order of maybe a few kilometers a second, which seems fast to us, but in terms of spectroscopic information and the light that we receive, it's dwarfed by a lot of other effects. So we've had to wait pretty much till now till that we can actually have instruments that can allow us to measure that effect. So it's just been one of those situations where we've known what to look for, but we've waited for technology to catch up. Do we think that there's any way to really measure what went on before the Big Bang? Actually, I'll say right now, no. But one of the questions that there are a few individuals now that are working on, they're asking themselves, are there imprints in, well, not in his primeval atom, but in the initial Big Bang itself, in that initial condensed state, that initial singularity, possibly, if singularities can actually carry information, that's the question. But some people are asking themselves, could there have been something imprinted from an earlier, pre-Big Bang epoch? And we don't know. Right now, we don't even know how we would begin to look for something like that. But there are some questions that we have that lead people to ask just the question that you do. Because one of the things, we've got galaxies, just like this one that you saw here. And when you look at galaxies, you ask yourself, goodness gracious, what made those things form? There must have been some kind of early disturbance that led to matter getting together and galaxies forming. Okay, well, if you look at the radiation, the hiss that's left over from the Big Bang, you find that it's remarkably smooth. Remarkably smooth. So how do you form galaxies? Even though we've seen slight variations, enough that could lead to some clustering, we still don't see enough information to tell us how galaxies formed without disturbing all this background hiss that's left over. And people say, maybe there's something that we can learn from that that will tell us about what happened before the Big Bang. So you ask a good question. Right now, I'll say, no, I was not implying that. And, but there are people, like I say, a few individuals that are starting to consider that question. Yeah. The question is, first, when we look at the background radiation from the Big Bang, first, if it came from a point, why do we see it evenly distributed through space? And the other question is, if the universe is expanding, or I think you stated the universe is expanding slower than the speed of light, why hasn't it already passed us? Why hasn't this radiation passed us? Okay, first, if you think back, sort of what we're talking about, is there a special place in the cosmos? When the Big Bang started, it started at a point in some space, not in ours, because our space didn't exist. So when that expansion started, it contained all of the Big Bang. So now, whenever we look in any given direction, we're going to see a remnant of that. And actually, it's all around you now. Big Bang radiation, I mean, when you go outside this room, you're going to be embedded in it. And the other question is actually a good one. When you ask, it's like, okay, let's say that the universe is actually expanding slower than the speed of light. We don't know that. There's a very good theory that explains away a lot of problems that we have with the Big Bang called inflation. And what inflation says is that when the universe was very young, we're talking about a tiny fraction of a second, it underwent a phase change. Just like if you have a liquid fluid that becomes a solid or vice versa, you have a change in phase. The universe essentially changed phase and it increased in size, a huge amount increase in size in a small amount of time. It exceeded the speed of light to do this. So we know that light in our universe seems to be constrained to always travel at light speed. But the universe itself, it doesn't seem that it might be controlled or constrained in the same way. Because inflation certainly poo-poos that. It really does. But that's a good question. Now, it's also true that when you look into this hiss, you do see two spots where it's not quite uniform. There's a spot in the heavens where it looks like it's a little bit warmer. And that's the spot that we actually find ourselves moving toward. Okay, because of this Doppler shift that we talked about. So we see that there's one spot that's a little bit warmer, and if you look in the other direction, you see that there's one spot that's just a tiny bit cooler. And that's the direction from which we're coming. So there are some small irregularities. Well, those are actually fairly large irregularities, but we do see some other gentle bumps and wiggles too.
Puts us back in the center again. From where we were coming, where we're going.
No, but that's just relative. Remember, the Doppler effect is relative, yeah. It's a relative thing. No, I'm not talking about absolutes. Yeah, it's just a relative effect. That's right. Anybody else that's moving through the cosmos is also going to say, oh, there's a hot spot. Ooh, there's a cool spot. Yeah. The statement question is that you had a universe that was born. It went through some inflationary period. Something happened. It expanded. It got very big. But as it expands, the expansion slows down. It's just like if I take this cap and throw it up, you can see that, well, maybe you can't see it up in the shadows. But as it goes up, it slows, it finally stops, and it comes falling back down. Is that going to happen to the universe? Right now, it looks like that's not going to happen. Because what we find when we start adding up all the mass, when you say, okay, I got all these stars, I got all this gas in the galaxies, I've got actually a large quantity of gas. It looks like most material is locked between galaxies, the intergalactic medium. If you add up all this stuff and include this mysterious stuff called dark matter, and we can actually make estimates for the quantity of dark matter in the universe based on gravitational effects. If you add up all of that stuff and you say, is there enough matter in the universe to actually stop its expansion, and does it cause it to come back down? The answer is no. Increasingly, we're finding that we are very close to a universe that seems like if I could take this and throw it at just the escape speed from the Earth, just 11.2 kilometers a second, if I throw it that fast, it's just barely going to make it away. And that's what it looks like the universe is doing. It looks like it's expanding. The expansion might, well, and I'll say something else here in a minute. The expansion is slowing, but it's slowing at such a rate that it's going to take an infinite amount of time for it to stop. And then you ask yourself, well, what does that mean? An infinite amount of time to stop? For all intents and purposes, the expansion goes on forever. Now,
no, because if I'm following your logic right, then that may be many zillion of years, but it's still going to. If it is slowing down, if it's decelerating, then eventually it's going to stop, right?
Well, but it's going to take an infinite amount of time. I mean, you can go a zillion years and you still have a long way to go to infinity. See, that's the problem. It's called an asymptotic solution. What you find is that we keep approaching a point where the expansion stops, but we never quite get there. We never get there. And can I just add one other thing that's really interesting is that Alex Filippenko, and who's at Cal Berkeley, and a few other individuals have made some, astounding observations of supernovae in distant galaxies. And what they have found is that, at least early on, the implication is that the universe is actually accelerating. Yeah. And that is something that people are just sort of slapping their heads and their legs and scratching in all and sundry places, trying to figure out why the universe would still be accelerating. What could do that? Remember the cosmological constant?
Yeah.
It's rearing its head again. That thing that Einstein said, oh, it's the greatest blunder. I made a mistake. I should have believed my math. Now, they're actually saying that the cosmological constant is not zero. To explain an accelerating universe, you actually have possibly another unknown fundamental force of nature, or something that we do know, we just don't understand, that's causing things to puff out in a way. Boy, we're living in very interesting times, just like the Chinese proverb, may you live in interesting times. We are in interesting times trying to figure out this. I mean, this has just come out within the last year and a half. It really occurred everywhere. It actually occurred everywhere. If you start trying to trace galaxies back in time, what you find is that galaxies themselves are communal objects. They don't like living by themselves. They almost always, unless there's been something that's tossed one out, they occur in clusters. And if you try to project back in time where a galaxy would have been, all you can actually project is where it was in the clustering. We can't even do that very well. Now what you can do is look at clusters of galaxies as a whole, and some clusters have thousands of galaxies. You can ask yourself, where was that cluster a few billion years ago? And even then, you find that you can't really get anywhere. You really can't. Because you can look at a universe that's much smaller, and it gets you no place closer. Because again, one of the things, if you think about the Big Bang, it occurred everywhere. I mean, it actually occurred everywhere, which is very intimate. I mean, it's really intimate. I mean, you and I, at the time of the Big Bang, our matter was in the most intimate embrace that you can imagine. I mean, we were just there churning away, and now we've separated, obviously.
I don't remember it.
Yeah. But really, but yeah, I wish we could march back, but it turns out that you can pick any place you want to and say, I bet the Big Bang started there. It did. Because all of the space that's around us, this nice, flexible space, I mean, it's just so nice, and black holes squeeze it and punch it, and galaxies cause little ripples and bubbles, and the sun even ripples it. It came out of that initial Big Bang too. So we really can't talk about a center or one distinct point, because everything was involved at the same time. All of matter and all of space. And time too, which is sort of a human creation, but yet it came from there too. Yeah, I think that's everything. But thank you very much.